Thanks for joining us, everyone. My name is Mike Staples. I'm a SOLIDWORKS application engineer with TPM. Today we're going to take a look at how students are utilizing SOLIDWORKS to create competition-winning robots. And today's files that we're going to be working with, the SOLIDWORKS data, has been donated to us by Yeti Robotics. So first, to get started, we'll tell you a little bit about Yeti Robotics. Yeti Robotics is a FIRST Robotics competition team that's based in Charlotte, North Carolina. FIRST Robotics students design and build a 150-pound robot to play sport-like games that change every year. This year's game is FIRST Stronghold, which is a castle-based theme that allows the students to drop gates, climb towers. There's boulders to shoot, moats to traverse, lots of different activities. And this season's build, nearly 6 months of hard work from very talented students and guided by dedicated mentors, concluded just 2 days ago, and competition begins next week. Today we're going to look at how SOLIDWORKS enables these students to design these amazing robots in such a short time frame. We'll break the demonstration into a couple of key segments that'll last roughly 5 minutes per segment. We'll take a quick recap at the end of each segment, and then again at the end we'll have an opportunity to answer any questions that you guys may have. So breaking it into 3 segments, the first segment we're going to address creating models of components, whether they're multi-body parts like you see in the frame example here, or individual parts. Typically we get a concept, we sketch it out, and then we start our 3D modeling. Once we've created some models, then we assemble components. So we'll have a segment that focuses on creating assemblies. And then lastly, we'll take a look at a segment that shows you how to leverage your 3D data. Obviously, we're talking about working with some pretty complex designs that have a lot of moving components and requirements. So taking a look at leveraging our 3D data to get the most out of our 3D information. So our first demonstration segment will go from a concept sketch of a layout of what the frame needs to look like for this particular design to a finished part that's ready to go into our robot. So to get started, we'll take a look just at the finished robot here quickly. We do have some moving components within our assembly. We do have some simulated real-world moving components. We'll take a look at the frame structure that we're going to be working with. So the frame is a aluminum extruded square and rectangular tubes. So regardless of the profile that we choose to use, the philosophy kind of goes the same. We start with a layout and then we start populating our structural components. So let's take a look at that. We'll start by launching a new part in SOLIDWORKS. And the approach that I'm going to show is slightly different than a traditional approach. This approach kind of allows you to do a layout sketch as you would normally do. But in addition to doing a traditional layout sketch, I'm actually going to start by generating a solid, and then I'll use that solid to generate my 3D sketch. It's a little different technique. One of our application engineers created a 3-minute Thursday video kind of showcasing this design process, calling it wicked weldments, wicked fast weldments. Okay, so I've got a kind of a base structure of the overall shape. This could be very simple like you see here, or it could be more complex. And the idea is we're next going to create a 3D sketch. We're going to select all the edges and we're going to convert those into our 3D sketch. So very quickly we have a nice layout. We can kind of hide away that body, get it out of our view, and we have a nice overall layout of the shape that we want to use. So some of this information may not be needed, so I'll keep it here just for reference, just for my own purposes. And next, there's some vertical support structures. So rather than doing any separate sketches, it's really not needed. If you're working with a three-dimensional sketch, very simple and straightforward to just go ahead and continue adding these sketch lines within your three-dimensional sketch. Okay, so in sketching in a 3D environment, we'll just pick up some relationships along various directions so that we can ensure these lines are lined up as needed. And if not, we can simply add relations. So in 2D sketches, we're doing horizontals and verticals. In 3D sketches, we're going along specific axes. So to finish off my sketch, we always want to use fully defined sketches. We'll go ahead and just add in a couple of dimensions here. So there's my complete layout sketch. Fully defined sketch. It's got all the information that I need. And again, it's going to be very simple to make changes later on. So structural members, when we have our layout sketch, then we go ahead and launch the structural member, and in dealing with weldments, we're able to pull from a vast library of the various types of profiles, shapes that we might want to use, such as I-beams and angles, square, round, rectangular tubing, things like that, aluminum and steel, all built together in a nice library that comes with the software. So in today's example, we'll start with some rectangular aluminum tubing. And when we choose the type of profile we're interested in, all the various sizes that are set up for that particular profile are listed, and you can choose from there. And ones that you use frequently will pop up at the top of the list. So to populate our geometry, we're just going to visually in the graphics area go ahead and select those sketch lines that are going to define the location of the geometry. If the profile isn't in the exact orientation that we need, so for example, if we want these vertical legs to be full length, we want this base structure to start out all the way down at the bottom here, we can simply locate the profile and choose a vertex from the profile to relocate things. Okay, so when I select that, notice everything shifts down, gives me a little bit of room there. Again, I can choose any of the vertices from that profile to relocate things. And when I want to add in additional members, so these long braces here, I just start a new group and make my selections. Again, we'll locate those to shift things down a little bit. And the nice thing about working with weldments, as I zoom in a little bit, you'll see the preview in yellow here. It's showing that it's going to automatically trim that back so that we don't have overlapping structural members. So with that first command, we've got all of our rectangular tubing laid out for the base structure. We'll do one more structural member so that we can add in all of our square tubing. Okay, so in similar fashion, we'll go ahead and select those sketch lines all the way around. Again, we can locate the profile if we want to push this up or push it down. So maybe we've got the overall height. I'll go ahead and push this down. And then another thing of note here is the treatment at the corners. So the software automatically is going to be trimming those corners up. So if I want a long beam going across the horizontal here, at any of these nodes I can simply just click in the corner and adjust so that this ends up being the longer beam and trims back this other segment. Again, we'll add a couple additional groups here for all of our vertical members. And as I'm populating those, take a quick look at the previews and you'll see that those will also be automatically trimmed at various lengths. Notice it's not going the full length of our line segment. It's going to automatically trim back at the top and bottom sections. So in very quick work, we've laid out kind of a base frame structure. So additional tweaks that we might want to do, for example, we may want to extend that lower base frame structure. The functionality is combined into a single easy to use command, trim and extend. So you simply select the pieces that you want to work with and then choose where you want to adjust them up to. So I want it to go all the way to this outer end face on this side and the other side. So we can see with the preview here that it's going to extend both of those bodies all the way up to those outer end faces. Pretty nice. Some more things we would typically add are materials. So let's go ahead and choose a material that we might want to use for this. Remember the body that we had created in the middle. When we go to do mass properties and things, we really don't want to have that body lying around anymore. So an extra little bit of cleanup work that I would recommend would be to just go ahead and delete that body as a feature towards the end. So it's no longer in the model, but the body in the history tree earlier on is still there. So all of the driving dimensions are still available. So let's say we want to make some quick changes here and adjust the length of some of these segments. We can take a look at the mass properties, and since we've applied materials, we can see the weight of our design, and if we wanted to monitor the weight of the design, we can create sensors to do that. Sensors can monitor values, sensors can monitor dimensions and various simulation results, and they can alert you as an option if this becomes greater than a certain value or less than a certain value. So if you violate some criteria, maybe in this example, 150 pounds is the maximum weight of the entire assembly. So obviously weight is a big concern for these robotics teams. So let's monitor the weight and make sure that it doesn't exceed 10 pounds. Okay, so the sensors will show right here. And again, as we go to make some design changes here, maybe we want to adjust the overall length. And as soon as we violate that sensor, we're going to get alerted. It throws out some big flags for us and alerts us, lets us know that we have exceeded what that sensor was set up to alert us for. Okay, so one last thing to kind of take a look at here is that when working with weldments in SOLIDWORKS, it automatically will generate a cut list for you. And it will group together like components. So any of these structural members that are identical geometry, they're going to automatically get grouped together as items within the cut list. And notice part numbers and descriptions, those are some values that we could enter in. If we want to take a look at the cut list table, descriptions automatically populate for us as well as the overall length of these structural members and quantities. So here's a preview of what our finished cut list is going to look like, similar to a bill of materials in an assembly, for example. So in our first short demonstration segment, we got a chance to see how SOLIDWORKS is extremely fast and allows you to create some incredibly intelligent designs that are easy to manipulate. In our next short segment, we'll take a look at how we can take some components that have been created and start building our assembly structures from those components. So back over to our main assembly. The assembly structure that we're going to be focusing on is the shooter assembly. So this is the central structure in the middle that has some systems here with motors and structures to grab the ball and shoot it up out of there. Okay, so for this, I'll start with a subassembly structure that's already been generated. This could be done in sheet metal and weldments, and we've got the subassembly structure already started. So we'll go ahead and launch to create an assembly. And with this assembly, it's really just a matter of browsing to the components that you want to add and drag and drop them in. Now, if these are frequently used components, and we'll get some messages here about the student version, since these are student donated files. So we get a nice preview of the components. If there's configurations, we get an opportunity to choose the appropriate configuration. And if these are components that we're going to use frequently, we would definitely build up a library. And within that library, we would add some mate references so that we could really just drag and drop them from here and immediately snap them into position. Okay, so these are, again, some components that were donated, so I don't have that extra level of intelligence built up in this, so you get a chance to see kind of the day-to-day process of any components that you've designed and getting those positioned in your assemblies. So the very first thing that I do when I'm working with an assembly is simply get the components placed in there, maybe move things around a little bit and get components rotated, kind of set up so that we're ready to start rocking and rolling positioning these components. Okay, so I'll show a couple of different techniques to start placing these components where they belong. And the first of those techniques is just kind of a manual process, just simply selecting the faces that we're interested in mating together and snapping them into place. Okay, so that's a pretty straightforward process. Select one, select the other, and you can go ahead and line up faces and holes and get things positioned appropriately. And again, it's a pretty fast process. Doesn't take too long. To speed things up just a little bit, we can grab edges and we can do kind of smart mating where we can drag components around and match up multiple faces at the same time. So we mashed up these two faces to be coincident and we lined up the holes all in one quick command. Okay, we'll take a look at the other side and get this guy positioned. So that last technique that I just showed is a very quick technique, very useful one. So we'll show that again here. So if we want to grab this edge right here, and as we drag that around, we'll just move it into position. And we now have that motor snapped into place exactly where it belongs. And again, there's no pre-setup work that's required to utilize that capability. And maybe we want to position this with a little bit of a distance down here. Again, we can do that on the fly and set up that distance value. So with just a little bit of work, we've got half of our assembly created, and of course any designs where you have symmetry, you can leverage that symmetry to populate things very quickly. So we'll take a look at the right plane here, and we will go ahead and mirror these components over to the other side. So as we go to mirror these things, one of the choices that we'll have is if we need a left and a right hand version of any of these components. So for example, this C channel is going to need an opposite hand version over on the other side. No problem. We can create that on the fly as we mirror components within an assembly. We can create left and right hand versions. We also get components fully positioned and we get dynamic movement. So as I go to test out the function of this design and rotate this wheel, we get the other side moving dynamically. So any changes to position, we truly have intelligence and mirroring, we have symmetry within our design. Now, taking a break from the symmetry, if we have other configurations, other versions, maybe we need a larger hole just in one side than the other, there's a configuration that's already been generated on that component. We can easily just switch a part over to that configuration. So with that, we have a fully created subassembly that we're ready to pop into our higher level assembly. So in that segment, you got a chance to see how we can leverage SOLIDWORKS to visualize exactly what our designs are going to look like and assemble components very quickly. In our next segment, we're going to take a look at how we can leverage this 3D data. So we've seen how we can create these assemblies, and again, this is a very complex assembly with a lot of moving components, a lot of intricate detail. There's over 800 parts in this particular assembly. And so we need to ensure that we have proper form, fit, and function. Maybe we have some functional stops built into our design, so as we rotate to a certain angular position, the components are going to limit the travel and stop it at various orientations. So we'll show you a couple of the tools that we can use to analyze the effects of motion within our designs. And again, we're kind of focusing on the theme of leveraging this three-dimensional data once you've created it. Now it's time to go ahead and leverage that 3D data to ensure proper form, fit, and function. So for this next portion, I'll hop into a section view where I've cut through many of the components, and we'll kind of focus in on the area where we have this shooter subassembly. And as I grab this guy around, notice the shooter subassembly moving around. And again, without the tools that we're about to show, it would be very challenging to make sure that there's no collisions in various regions of our design, and to figure out exactly which faces are going to start touching first and ensure accuracy. Okay. One other thing that I do want to show, though, as we go to do this segment, is we mentioned sensors a little bit earlier on. So I'll create another sensor here, and this sensor is really to measure the angle that we have for this particular shooter assembly. So maybe our design criteria is that it can go between 5 and 40 degrees, and we need to ensure that. So right now it's measuring at 16 degrees. We can take that measurement and generate a sensor from that measurement just by simply saving it and choosing what information we want to capture from that. We'll go ahead and generate that sensor. So again, the sensor will show up at the top of the tree here, giving us the accurate measurement. And again, it's just going to monitor that. I didn't set any alerts. I just want to take a look at that value real time. So as we go to move that component, I'm going to turn on an additional option. Instead of just dragging it around, I want to look for collisions within my assembly. I can look for any collisions, or I can get a little bit more specific and say I want to identify anywhere between the chassis and the subassembly that I'm finding a collision. Okay, so as I start dragging this around, we'll get alerted with an audio alert. We'll get visual feedback. I'll zoom in here so that we can see exactly where that collision is occurring. Because again, looking at a complex assembly, it's not all that intuitive and obvious to see exactly where we're going to end up with these collisions. Okay, so as I rotate this upwards, we can see that these two blue brackets right here are highlighting in this bright blue color, indicating that they are colliding with this outer bumper structure. And if I leave the assembly exactly where it is and just rebuild, I'm going to immediately get some feedback here telling me that that angle is now 44 degrees. So again, we can kind of verify if that meets our design criteria. And checking the other location, so that side was probably pretty obvious that there was a functional bumper that was going to stop the component's range of motion. Going to the lower direction, though, it's really not obvious exactly what's going to collide, how this design is going to function. So as I start approaching, I'll go ahead and zoom in a little bit tighter here. As we start approaching, we can see the highlighted faces in bright blue. The highlighted faces of the cylinder is actually what's hitting. Okay, so again, we can evaluate our design and we can see, is that the intended stop? Do we need more range of travel? Do we need a functional stop designed into this where we've got some plates hitting instead of these cylinders? I'll go ahead and hop out of this and we'll update our sensor again that's monitoring real time. Lets us know that our lowest angle that we can drag this subassembly down, we can retract this subassembly, is going to be 4 degrees. Okay, so in that segment we saw just one of the many tools that we can leverage within our 3D designs to be able to ensure that we get our designs right the first time, whether it's looking for collisions or interference among static components, collisions among dynamic components moving around, or maybe some misaligned holes within our assemblies. We utilize the evaluation tools that are built into the software to check form, fit, and function and to ensure accuracy before we start cutting seal and getting to the prototype phase. So in summary, we got a chance to see a couple of short areas of common design work within SOLIDWORKS, and we got to see how SOLIDWORKS is fast. It's a great visual tool, and it allows us to be extremely accurate in our designs. So with that, I want to thank you guys for attending today's webinar.